But here's a mic.
Oh, great. Gotta put my props on. I've got a belt, don't I?
Hi, I'm Benjamin Satterwhite. I'm the planetarium. So it used to be a third planetarium, so you guys may have visited it. We in conjunction with this year kind of started another community show. So we're doing third Thursday out at the Twin Checker Planetarium. If you're at our last show in September, it was packed full of children. and was mildly unpleasant for some of the adults. So we have swapped up. We now have two shows. We're going to be offering a 6:30 kids show and then a 7:30 adult show for you guys. It's free to the public. It's going to be October 20th. Yeah, so for most of the folks in here, 7:30. Come on out. We do a little bit of stargazing, and we try to tie in a little bit of the information from these lectures into it as well. So you'll get to see what you can observe. We got about 45-ish.
No expense spared.
If you guys want to come out, I'd love to have you.
Thank you.
So, Community Checker Planetarium is in Capitol High School, which is out on Milwaukee and Goddard. You can find our website underneath the Capitol High School head. Community Checker Planetarium that should show up.
It's my great pleasure to introduce Professor Guy Worthey from Washington State University.
Thank you. Thanks.
He is a world expert for galaxy formation. So I'm so excited he's giving us this talk. He developed a software. It's basically like Facebook for galaxies. Everybody uses it, like thousands of millions, maybe thousands of users. And then it's fair to say that software transformed the field of galaxy formation. I will spare you the details, but it's just such a transformative software to our field. And his website is also a treasure trove for galaxy formation. Please check it out. And Professor Worthey is in charge of James Richard Lewis Observatory, the largest refracting telescope in the state of Washington. He's also in charge of the Washington State University's planetarium. And I saw he has so many impressive shows. I'm so jealous. So if you get a chance, please stop by Pullman, Washington to check out Guy's planetarium shows. And outside astronomy, Professor Worthey has published a few fictions. And just to quote his Amazon author page, Wyoming native Guy Worthey traded spurs and lasso for telescopes and computers. But he decided to pursue astrophysics. I will spare you. You can Amazon Dr. Worthey and read the rest. It's awesome. Please join me in welcoming Dr. Guy Worthey.
Thank you, Heidi. And thanks for inviting me. This is great. This is great fun. Guy Worthey couldn't make it tonight. Instead, we have Guy Uvar, light detective. It was a dark night in a universe that knew how to keep its secrets. But on the 9th floor of the Webster Building, located in Pullman, Washington, a light still burns. One man's trying to find secrets to life's persistent questions and also how the universe put itself together. So, welcome to tonight's installment of Guy Uvar, Light Detective. Not quite done here. Applause would be okay. So tonight I might have to lose the coat eventually. We'll see. We'll see how hot I get. But the tonight's episode is the mystery of galaxy formation. So we're going to apply our knowledge to those pretty things in the universe. These are galaxies. And we know a lot about galaxies. We can count them. We can see them come and go. We can see what their shapes are. Here's this beautiful spiral galaxy. This one's always inspirational, but they don't always come flat and round like that one. This one is sort of schizophrenically flat and round at the same time. So this one's a lenticular galaxy. Lenticular meaning lens shape, same word root there. And we have galaxies which are just round balls. We call these elliptical galaxies. They don't have any spiral structure, they don't have new stars, and they don't have any gas. We also have galaxies which are interacting. So here's an example of an interacting galaxy. And galaxies like company. So we find galaxies also in groups. So here's a smattering of the one of the central bits of the Virgo galaxy cluster. So we can count them, we can measure their brightness, but we would like to know more. We'd like to know what they're made of. And the light you see is almost all star light. So they're made of stars. The stars are ordinary stars. A lot of them are like the sun. But the difference may be, differences that may exist might be interesting. And they might tell us how these galaxies were formed. And we would like to know that story, because knowing stories is what detectives do. But we need optics. That's what that cartoon is reminding me. Our eyes are not sufficient. Our eyes can see a few galaxies, namely 4, the Milky Way, the Andromeda Galaxy, and the large and small Magellanic Clouds. So we can see 4 galaxies with our eyes. The rest, we need optical aid to do that. So we're going to take a little side trip into light. So here's a spectrum of light. So you see that rainbow across the top there. So that's you see that a lot in rainbows, for example. And also, if you were to take a prism and string out the starlight that comes from the sun, that's what you would see. And a cartoon of an early light detective there is on the bottom. That's Joseph Fraunhofer. And he took a particularly steep prism, and he took sunlight and he looked at its spectrum. He didn't see exactly this. He saw something similar, but not exactly this. And before we leave this slide, take a look at, there's some numbers along the bottom. Those are wavelengths. And light is all the same stuff, but the only difference between blue light and red light, for example, is the wavelength at which it comes. In the early days, they thought that light needed something to travel through, like sound waves do, but that turns out not to be correct. Light can travel through a vacuum as well. So what Fraunhofer saw when he looked at the sun was more like the top of this slide. So this is the solar spectrum over that range of wavelength from 400 to 700 nanometers. And he saw the wash of colors like you're used to, but he also saw these dark bands. And those are very interesting. So these dark bands happen at specific wavelengths. And we soon learned what a lot of those lines stood for, or what was causing them. And they are from various individual elements and sometimes molecules in the spectrum. The top row of letters, that's what Fraunhofer himself called these lines. But then we have since subsequently learned where they came from. For example, the G band is from the molecule CH mostly. And these lines called K and H, those are from calcium. And not just any calcium, but calcium that's been ionized once. So it's missing 1 electron. And this little b right here in the middle, that's from magnesium. And we've got hydrogen in there. And we even have some what do you call it, imposters in there. We've got a couple of lines here that aren't from the sun at all. These are from the atmosphere of the Earth. So there's a couple of oxygen bands in there, the A band, the B band, and we've got a little bit of water vapor as well that eats up a little bit of light at just specific wavelengths. And that's kind of the key here, because if you've got a fingerprint, as detectives know, if you've got a fingerprint, you can make identifications. So we can see these elements in the sun. We can see them in stars. And because galaxies are made of stars, we can see them in galaxies as well. The bottom is just the same picture, but arranged like an astronomer would look at it today. So you just plot intensity versus wavelength and you get this wiggle. If you were Fraunhofer looking with your eyeballs, you'd get some smear that looks like that. But the features, H beta, magnesium, they all show up the same way, whichever way you do it. So Fraunhofer learned two things. One was that the spectrum was full of features. So, and we could identify a lot of them even early on in the 1700s. The other thing was he put his thermometer redder than red. So he moved his thermometer and he caught some heat from the sun in the spectrum, but then he moved it even further and he still got heat. And then he tried the other end of the spectrum, bluer than blue. He moved his thermometer over there and he still got heat there too. So Fraunhofer also learned that what we see isn't all there is. There's a lot more to be seen. So bluer than blue, we call that ultraviolet, UV. The part we see, we call that optical. And then the part that is redder than red, we call that the infrared. So that was the start of this timeline here, this wavelength span up here. This is the electromagnetic spectrum, all of it. And it's got ultraviolet, optical, infrared in the middle. And then to longer wavelengths, we have things like microwaves and radio. And then to short wavelengths, we've got X-rays and gamma rays. You'll notice there's kind of a thrill of fear when I say gamma rays and X-rays, and that's actually correct. You should be afraid of them because they actually are dangerous. In high dosages, they are dangerous to human beings. The bottom of this picture shows that from planet Earth, from where we are, we can see pretty well in the optical, and we can see another clear window in the radio. But other wavelengths are in large part blocked by the atmosphere. This is excellent for screening out gamma rays and X-rays, but it is less than convenient for astronomy. So we want to invent other ways to do that. Of course, we have done that. So we have built all kinds of different telescopes. Here's a few of them. So on the right are the Green Bank radio telescope and kind of an optical observatory mountaintop thing at the bottom right. We've got Hubble Space Telescope in the middle, which sees mostly optical, but a little bit into the ultraviolet and also infrared. On the left, we've got James Webb Space Telescope, Chandra X-ray Telescope, and Sophia Infrared Telescope, which I didn't realize until after I made the slide, but Sophia has been grounded. It's done. The mission is over. So it's a 747 with a telescope in it. How romantic is that? It's really cool. Almost as romantic as detectives. So let's go galaxy hunting. Let's try to figure out some things about galaxies. So here's the local group, we call it. So this is the Andromeda Galaxy in the middle, or M31. And next to that big galaxy, the Andromeda Galaxy, we've got a couple of satellite galaxies that have drawn our attention over the years. M32 is a small, compact galaxy. M110 is a slightly less small, the elliptical galaxy. So those three galaxies crop up now and again. This is a ground-based image in the optical, but what if we used Hubble Space Telescope? So let's go ahead and use what we've got. So let's use Hubble Space Telescope. Let's zoom in right there. Hubble Space Telescope is excellent at looking at really tiny bits of sky in great detail. So here we have an image from the advanced camera for surveys. You'll notice in this picture some pretty bright stars. Those are local. So those are nearby stars that got caught in the field of view. And then you see at the bottom, you see this brightening And that's the galaxy M32, starting to get toward the nucleus there. But then in the middle, you see all this speckledy stuff. And that speckledy stuff, let's zoom in one more level. That speckledy stuff is all individual stars. So point at one dot, and it represents a giant star, very luminous star in this area of sky belonging to M32, or possibly M31. Whichever choice you make, they are about 2 million light years away. So Hubble Space Telescope can get at least the brightest stars from enormous distances away. But they're ordinary stars composed of ordinary stuff. There's a couple of places in here, and the audience in the room will see my laser pointer. There's one right here, for example. That little guy is a star cluster. So that's a patch of stars that formed all together and has stayed together under the influence of gravity. So that's a star cluster. We have such things nearby as well. So we have local star clusters as well. Here's a couple of examples of them. They also have M numbers. We have M71, M50. They look different, don't they? Look different. They have kind of two styles of star clusters here. We have globular clusters, which look like M71. They are massive. They're dense. Thousands to hundreds of thousands of stars in globular clusters. And when we look at their ages, they turn out to be old. We'll talk more about age here shortly. They're pretty rare. We only have 160 objects like that in the whole galaxy. Open clusters, we have thousands of them. So they're very common. They are much lower mass, from say dozens of stars to thousands of stars, rather than thousands to hundreds of thousands. And some of them, not all of them, but some of them can be quite young in age. And so our Milky Way is composed of stars which we think all started as clusters, and then the clusters fell apart and became the stars we see around us in the Milky Way. So now let's get to age, and this is how we do it. So this is how astronomers look at star clusters. So here's the seven sisters, they call it. This is the Pleiades. If your telescope operator is kind to you tonight, you will see the Pleiades. It's a fall object in Taurus, the constellation Taurus. It's very pretty. It's got some hot blue stars in it. And how an astronomer charts this out is by looking at each star one by one. So let's take the brightest Pleiad. Its name is Alcyone. And let's make a plot. And this is called the HR diagram, or a color magnitude diagram. And let me walk you through the things that are on it. You have to learn science because we're at a science talk. You're apprentice light detectives tonight. What we have down here could be temperature. If it's temperature, then the cool stars are on the right. And I actually have some numbers along the top axis here to indicate temperature. So cool for a star is 3000 Kelvin. That's cool for a star. And then a hot star is more like 30,000 Kelvin. So there's a pretty big factor of 30 in temperature. This is surface temperature, how hot it would be if you were to go to the glowing parts on the surface. It also translates to something we call color. And so blue colors are hot at the surface, and red colors are cool at the surface. And that brightest Pleiad, Alcyone, happens to be quite hot. And so it's toward the left of this diagram. And then up and down, that's how bright the star is. So there you go. The more light the star outputs, the higher it is on the diagram. So there's Alcyone, very hot and very bright star. So let's take the next few. They're also quite blue and quite hot at the surface. And all of them are pretty bright. And then we can keep going. So down to stars which you can see with your eyes, and then more stars that you can't really see with your eyes. So you need some telescopes to get you the information. And if you go all the way to pretty faint stars, we get a whole row of stars like this. So these are all the stars in the Pleiades. Maybe we're missing some at the very faint end, because those stars become so faint they're hard to spot. Do you see order in this chaos? There should be a very, very striking main sequence, we call it. So there's this main sequence of stars. And then what happens with stars that are on the main sequence is they're like the sun. So the sun is happily burning some hydrogen at the center. It's becoming helium right now, and that supplies the sun with all its power. The sun would appear on this diagram right around absolute magnitude 4 and 4.7, somewhere in there, and B minus V about 0.67, right in there. So the sun, a solar analog, would be right about here. So you see the sun is right about in the middle of things. It's neither cool and faint, nor is it bright and hot. When those stars run out of fuel, though, well, they will eventually, they start to evolve. They will become they'll become brighter, usually redder, and they might even do crazy things like becoming giants or supergiants, and eventually they will either blow away their outer envelopes, or if they're supermassive stars, they will supernova. So catastrophe is in their future. When they do that, you can tell they kind of leave the main sequence. So there's this area where these stars are becoming too bright for the main sequence. Question? That's an excellent suggestion. The answer is sometimes. Great. Now it's permanent. And now I got to click. Another nifty thing, let's just store this bit of information for later. Another nifty thing is that stars, we know a lot about stars. So we can take either a spectrum of that star or compute a spectrum for that star. So this happens to be a computation for the spectrum of a blue star in the Pleiades. And so for any place along that sequence, we can take an example star and make a spectrum, or we can compute one until we've got all of them if we want there. So we have 3 regimes. We have ultraviolet, optical, and infrared. And that's my name. I'm Guy Uvoar, light detective. You'll notice the blue stars are they emit in the ultraviolet. So let me show you that, right? If you go to the ultraviolet for this blue star, there's a lot of stuff there. But then by the time you get to the red star, not so much. It's all damped down. So hot stars are blue, and they emit in the ultraviolet. The other cool thing about the main sequence is that it translates directly to mass. So a really big star, a massive star, when it's first formed, is going to land on the main sequence, but at the top left. So it's going to be very bright and very blue when it first forms. And so on and so forth. We've got a very lightweight star. It's going to land in the bottom of the diagram. So following the mouse, that's 10 solar masses up there. And by the time you get to 1, that's the sun. And then by the time you get to the end, that's about 1/10 of a solar mass. And I've also marked lifetimes here. So the more massive the star is, the brighter it is. So the faster it burns up its fuel. So these 10 solar mass stars only live about 30 million years, and then they pass on. They go to their end state, whatever that might be. And you can see those numbers increase. So 5 solar masses says 180 million years, and then 3 solar masses says 640 million years. Then we switch units on you. 2 solar masses, 1.7 billion years. And then 1.5 solar masses lives 3.6 billion years. And finally, the sun lives about 10 billion years. So the sun's age presently is 4.5 billion years. So it's about halfway along in its lifetime. If you get much less massive stars than that, they live longer than the universe does. And so they are not going to evolve in the lifetime of the universe. So with those numbers there, you can see that, oh, maybe since the Pleiades has already lost its 10 solar mass members. Can you see the ghost of the Pleiades in the background there? So any stars that used to be 10 solar masses in the Pleiades, they're gone. So we can tell the Pleiades is older than 30 million years. And then we can judge, just fitting by what we know about physics and stars, we can judge the age pretty well for the Pleiades. The Pleiades is about 100 million years old once you do the analysis. So if all stars in a galaxy started in clusters, and clusters have a certain age, can we not do an analogy where if clusters make a galaxy, can we then add up together a bunch of spectra and make a model galaxy? The answer is yes, if you're a light detective. So here's our kind of our analogy for how to make a model of a galaxy. And not a model physically, right? But a model of the light coming out. So now you've done it. You've made a light model. So here's another spectrum. Infrared, optical, UV, and we've got 2 ages of galaxies here. We've got a 3 billion year old galaxy and an 8 billion year old galaxy. Of course, they're not galaxies. They're just products coming out of your computer, but they are indicative of what your galaxy spectrum might look like in broad brush. This is a huge bunch of wavelength here. So it's a big bunch of spectra. So our analogy is this. If you had a galaxy in the sky and a telescope with a spectrometer, you can get a spectrum. And then if you've got a computer with stellar evolution code in it and some stellar spectra that you can either calculate or observe, and then you add this code, I've said IMF. That's just a shorthand for how many stars at which mass is going to form. And the answer is lots of low mass ones and very few high mass ones. So if you had those 3 ingredients, you can make a model spectrum as well. And then you got 2 spectra. You've got a model spectrum and you've got the observed spectrum. So you can compare the 2 and detect to your heart's content. Types of questions we want to answer are when the stars formed in those galaxies. Recently, long time ago? Don't know. We better analyze it and find out. And how much heavy element content do these galaxies have? Is it a lot? Is it little compared to the sun? What's going on with that? And there's lots of processes we see, or at least think we see, in the universe, such as merging of galaxies. And we think we might see the star formation quenching in certain environments like galaxy cluster environments. We expect that gas is going to drizzle into the galaxy. Is that really a thing? You know, does gas keep on drizzling into the galaxy and make more stars all the time? And then finally, there's this possibly I have the word morphology here. That's the spiral nature of a galaxy versus the lenticular nature of the galaxy versus the elliptical nature of the galaxy. Does that have something to do with the other things? So those are the kinds of questions we'd like to know. Some of this we can get. So this is not the only field of astronomy here. Some of this we can get by counting and by charting out numbers of galaxies of different types. So it's not happening in a vacuum, but it's pretty cool, this particular method. So success, I've got some models now, and let's take a look at model output. What's this? It's another spectrum. Oh, get used to it. It's going to happen a few more times. So here we have blue light, and then we have a red light over here, and we have we start with a model that's 5 billion years old and a little bit less metal poor than the sun. I've used some advanced code here for you, so I'll just translate it for you. If this crazy bracket FU over H thing was 0, that would be the same as the sun. If it's a little bit negative, that means it's a little less metal rich than the sun. So we're talking elements that are heavier than helium. Astronomers are funny that way. So let's age that model by a factor of 3. If we do that, we get the bottom wiggle. Or alternatively, let's take that model and increase its heavy element abundance by a factor of 2, in which case we also get that second trace. And I submit that that's kind of a bummer. In other words, those two bottom spectra are really hard to tell apart, despite the fact that they differ in age by a factor of 3, and they differ in heavy element content by a factor of 2. And that's actually quite disappointing. This is called the age metallicity degeneracy. And this is the type of thing that makes a detective want to hang up his fedora. Call it quits, retire. You know, there is some island called Bermuda. I've never been there. Maybe I should try. But no, that light on the 9th floor of the Webster building, that keeps burning. Keeps me awake at night. What can we do? How can we break this age metallicity degeneracy? Because I want to know the age. And that problem prevents me from doing that. Well, enough coffee and enough donuts, and you're able to overcome these difficulties, at least somewhat. And the idea occurs, well, maybe don't look at the whole spectrum, maybe just zoom in on parts of the spectrum. So let's look at the little bitty bits in the spectrum, and maybe there's some clues in there. So here is, yes, brace yourself, another spectrum. And this one is it's an example spectrum of just the blue part of the spectrum for a star. And the starlight you expect is on the bottom. So here's this wiggle with a bunch of stuff in there. Don't worry about the bunch of stuff. With the other things are the labels for what happens to the star, or what parts of this spectrum on the bottom are due to just the element chromium, for example. You can do this because chromium is just an atom, and you know all the transitions in the atom, and you can predict where those absorption lines are going to be. And it's always the same for chromium. The wavelengths are always the same. Calcium's even more emphatic, right? And then if you increase the nitrogen abundance, you're going to get the big feature there at 4,100 angstroms. So using this logic, we measure these little bits instead of measuring the broad brush item. And when we compare, we get diagrams like this. Now, okay, let's slow down. It's not a spectrum, but there's a lot going on. So let me explain what's going on in this particular diagram. This is for M32. So there's the phone number. It's this lovely little elliptical galaxy. And the symbol that's a dark triangle there, that represents the center of the galaxy. And then this tail is going further and further out in the galaxy. So now we're charting out kind of the radial, kind of the map of how the population changes as you go from center to the outside. And the rest of it are the improved models with the little bits, measuring the little bits of the spectrum. And one little bit is called H beta. So that is this y-axis up here. And then the rest of the x-axes are individual elemental features for magnesium, iron, iron again, and then carbon. The models are on here as solid lines for different ages. So you can see this is 2 billion years, 3 billion years, 5 billion years. 2 billion years, 3 billion years, 5 billion years, and so forth and so on. And then the dotted lines are different metallicities, so heavy element content, where the one in the middle is solar. It's a dotted vertical-ish line, and that one is solar. M32 never drifts very far from solar, no matter which element you consider. It's a little bit more than solar for iron, and a little bit less for magnesium, and a little bit more for carbon. And its ages is there too, and that's pretty consistent as well. It's around 4 billion years old. So wow, hold on, we did it. We did some light detection here. We found out that this galaxy, most of the stars in this galaxy formed at about 4 billion years ago, about the time our sun was getting together. And its elemental composition was also pretty similar to the sun. So we actually did some good by doing this. Yes. Or maybe not. So let's look at these two bits here. We've got an iron bit on the Y, and we've got a magnesium feature on the x-axis. And the models are here as lines. And they're at different metallicities and ages. Ages and metallicities, according to the age metallicity degeneracy, run about the same direction. So heavy elements and age have about the same effect on the spectrum. And then, what do the galaxies do? The galaxies say, I don't like your models. I'm going to go over here. How insulting. But it's a clue. It's a clue about galaxies. And the only possible explanations to move galaxies off the model grid like that are either an increase in magnesium abundance or an increase in iron abundance. But those vectors are really pretty solid. We're measuring a magnesium feature that's due to magnesium. So it's basically tied to magnesium. And then the iron feature is also similarly going to increase if you increase the iron abundance. So what happens here is that these galaxies, which are, by the way, now they're big. The galaxies are big. M32 is still on here. It's an asterisk way down here. So in the bottom, so that's our little galaxy we did before, which was about 4 billion years old and solar. So you'll notice that if iron's just a little bit more than average and then the age gets young, you can fit that galaxy with a young age. The rest of these dots, though, those are big galaxies, mostly elliptical and lenticular galaxies. And those galaxies appear to require more magnesium in order to fit these models. So that's kind of weird. So now this universe of galaxies we've got, ones that are small, have element mixtures like the sun, like we have here locally in the Milky Way. But then the big galaxies, the big ellipticals, massive ellipticals, they have more magnesium. It's kind of weird. Same iron, but more magnesium. So here we are so far. We got mean ages now. Yay. We find out that elliptical galaxies are really old. Spirals are not. Spirals like the Milky Way, are always forming stars, and so they kind of simmer along with new stars all the time. So they're a little harder for me to analyze. And we found out that the bulk heavy element abundance is also pretty big, and also a little bit bigger in elliptical galaxies, but not iron, and not elements near iron, but only magnesium, sodium, carbon, nitrogen, oxygen, some of the lighter but still heavy elements. So lighter heavy elements. So that causes a question which still haunts me to this day. So how does this galaxy choose to follow that pattern? What makes a big galaxy different from the Milky Way in terms of how it forms such that it gets a different metallicity mixture? Well, metals come from a couple of different ways. Let's see if we got the confusing plot of amazingness here. Here it is. So here's a periodic table of the elements, sort of, but it's color-coded by the 5 main mechanisms by which heavy elements are created. Number 1, we don't worry about too much. Only it says Big Bang nucleosynthesis at the top. And if you look for the color black, you find out that only hydrogen, helium, lithium, beryllium, boron have significant contributions from Big Bang nucleosynthesis. The green stands for evolved giant stars, which manufacture some elements in their cores, and then they blow them away. The blue ones, that's the exciting supernova you know about. So those are the big massive stars that go kaboom in blue. Red are supernova that start as end states of other stars and then explode from there. So there's a little difference, and there's a little bit of a time delay in the creation of those guys. And then finally, neutron star mergers. That sounds like fun. They're purple. You notice there's not a lot of that purple color on this particular diagram. This is due to some modeling by Kobayashi. The other cool thing about this picture is that each square is a timeline. So he's got a model where the beginning of the universe is on the left edge of each box. And then where we are in time is a dotted line about 2/3 of the way along. And then he projects into the future a little bit. And then the amount that we measure is the horizontal line. So let's look at carbon, for example. Carbon, the amount that we measure is really not fit very well by his model. So oops, he missed. This is totally usual for this subject. It's really hard to predict how much heavy elements come out. And that's why this question still haunts me, is because for a lot of these boxes, we don't have the right answer. We can't predict very well how much heavy stuff comes from these various sources. So that's all. I mean, there's so much I could go back at the end of the talk and you can look at this diagram again because it's fascinating and you could stare at it for half an hour. But for right now, let's move on. So there is this question, what's new, pussycat? What is the future of this particular subfield in astrophysics, where you take a spectrum of a galaxy and you try to pick it apart into galaxy formation tidbits? And I have at least one front burner project I'd like to tell you about in about 2 slides. And it involves going back to the Pleiades and looking at this main sequence again. If you look along the Pleiades, you can find some stars in a pretty narrow temperature range. And if you look at that temperature range, you find that some 15% of those normal stars are not so normal. they're chemically peculiar. So in that sort of cyan colored region, you can find what we call Mercury manganese stars. Sounds very romantic, doesn't it? The Mercury manganese stars have elevated abundances of, you guessed it, mercury and manganese by about, yeah, no, I'm not kidding. I'm telling you the truth. And the abundances are quite startling. You can have a factor of 1,000 increase in the amount of heavy elements you've got. And this is not because the star is different. If the star was really like this all the way through its volume, it would blow all our theories away. But in fact, what we think is happening is that the light that's leaking out through the outward direction in these stars is lifting those complicated atoms up to the very top of the atmosphere where they get concentrated. Rotation destroys it, convection destroys it. There's plenty of reasons why all stars don't do it. But if you have a really quiet star, this mechanism can come into play and you can get these chemically peculiar features to show up. And I have to show you one more spectrum, which is a normal star versus a Mercury manganese star. So normal in black and Mercury manganese in purple. You can see they're different. You don't have to look too much at that figure to figure out the Mercury manganese features are very, very strong. So my what's new pussycat front burner operation now is to try to use Mercury manganese stars and its relatives to try to get better ages. So its relatives include helium strong stars, helium weak stars, Mercury manganese stars, A metallic stars, and AP stars not pictured here. And the idea is that as that main sequence unravels, and you know the direction it goes, so the youngest populations have the bluest stars, and then as you age, it unravels. For a while, you're going to get helium strong stars as dominant, and then they're going to all evolve away and disappear. And then you'll get helium weak stars for a while until they disappear with age. And then you'll get Mercury manganese stars for a while until they go away and you get AM stars. So you can kind of see there's a pattern here. The bad news is that they're always not very, they're always 10%, 15% of the population of stars that are there. So they're not the only type of star that's there. So they get diluted, their light gets diluted. But if you had really good spectra, you could still find them if you're a good light detective. So I'm hoping that we are able to do this. And we've got one result anyway from applying this technique to this M110 object. So M32, we've got a good mean age of 4 billion years. We've got M31, which we know is pretty ancient in the middle parts anyway. And then M110, we've got now, I've been applying this technique as best I can. And I've got 3 episodes of star formation isolated pretty well. So M110 there in the corner, we think it's got a pretty specific here, 68 million year component, which is not a huge percentage by mass. It's only about 5% by mass. And then we've got a really heavy component at 1850 million years, so 1.8 billion years. And that's a pretty heavy and weighty component. And then the rest is going to be ancient, and we couldn't tell the age about that bit very well. So we have at least partial success in applying this technique. So I hope to take this sort of 3-binned, young, middle, and old scheme and dice it up even further. And pretty soon, I hope that we can take these spectra and really dissect them and find out a whole age history, and hopefully along with it, better information about the metal content as well. And so I know we're a few minutes early, but that's fine. Just want to leave you with the thoughts that we don't have all the answers, and maybe we never will. But one thing's always for sure. On the 9th floor of the Webster building up there in Pullman, there's always going to be a light burning on the 9th floor. But for now, I'm signing off, and I'm Guy Uvoir, light detective. I had fun. I don't know about you guys.
Yeah, so Guy, going back to that M110 result you had there with the 3 different star forming episodes, is there any indication of those being mixed together spatially or separated spatially?
They are definitely separated spatially, but spatially. So we were looking at just at this central kind of star cluster-ish region in the middle, which happens to be the brightest part. And so that's the easiest to observe. But we know that that bunch of B stars that's there does not extend past there. So if we were to repeat this with better signal further out, we'd get way different answer.
Different results from Earth-based telescopes compared to space-based?
So far, the only telescopes capable of spectra this good are on the ground. So space-based telescopes are great, but they are small. And this takes big telescopes. So we don't know yet. I presume no. I presume we'll get the same results no matter how you do it. That's a lovely thing about science. Yeah, question over here.
Earlier in the talk, you mentioned a group of stars that was once clustered and grew apart.
Mhm.
Is that due to just the expansion of the universe, or what physical mechanism explains that?
Yeah, let me repeat. That's a great question. So I'd mentioned something about clusters, star clusters that then fall apart and evaporate. And the question is, what's the physical mechanism for that? And does it have anything to do with the expansion of the universe? That last bit, no, it doesn't. It's not the expansion of the universe. What you have is a bunch of stars orbiting the common center of gravity. And you might lose one, though. So by random chance, you might have a little gravitational encounter between a couple of stars, and one goes away. Well, that decreases the mass of the cluster by a little bit, which means it's more likely that you're going to lose stars. And that goes on. The more stars you lose, the more likely it is to lose more. So that's the mechanism for doing this. And you've actually seen a cluster with your own eyes that has fallen apart. If you look at the Big Dipper, 5 of those stars, there's 7 there, 7 bright ones, but 5 of them are called the Ursa Major Moving Group. And they are members of a group that was born about 2 billion years ago, but is no longer a cluster. They're spread out all over the sky. They thought for a while Sirius was also a member of this moving group, but it probably isn't.
So that side of the galaxy that you consider ancient, and you're not able to quite figure out the age of that, is there a correlation between furthest galaxies to the closest galaxies to us to help you show an age?
Yes, through like an entirely separate logic chain. Absolutely. So just the existence of galaxies that are at high redshift means they started forming shortly after the Big Bang. So there has to be ancient stars that were formed way back then. And so today we'd still see those stars. They would be quite dim, and they would have turn-off masses around 1 solar mass. And we would therefore struggle. If there were other components that were younger, we'd struggle to see those really old stars because they're so dim. Yeah.
Is there any way with this technique to account for mergers of galaxies that we can't necessarily see? Something like if an elliptical was formed by a merger of a couple of galaxies, can we differentiate between a young galaxy, an old galaxy coming together?
That's exactly the goal. So we would love to be able to date mergers, starting with ones we know merged. We can see other evidence that they merged fairly recently. We'd love to know their age structures in there. And then for galaxies that just look innocent, are they so innocent? Or did they have really big, splashy, messy, opposite of divorce, I don't know, marriages? That was a hard opposite to come up with. But yeah, did they have messy mergers in the past? So that's exactly where this technique is going to shine, if I can pull it off. Yeah. Yeah, the question is, does red shifting and blue shifting play a large role in the data? The answer is yes. Maybe I should rephrase that as, oh, yes. One thing that is quite irritating about Doppler shifts is that for a big galaxy especially, those stars are all moving. And so if you look at an elliptical galaxy, you've got stars coming toward you, stars going away from you, stars going sideways. And so it all messes things up with the Doppler shift, such that the little tiny features that I'm most interested in all get smeared off and you can't really see them very well. So that is probably the biggest problem in really solving this for big galaxies. We might have to give up on big galaxies. Small galaxies are tamer and you can see the sharper lines. And so we probably have better success with spiral galaxies and dwarf galaxies. What a great audience. Thank you so much.
Mhm.